Subhashree used to be a PhD at IISER Mohali with Dr. Abhishek Chaudhary. In fact, back when I was there, that's when the paper came out. I presented the same paper at like a seminar delivery course at IISER Mohali, and when we were coming up with the idea for this event, I thought back to it and was like, of course, I have to ask her to come and present this. She's now a postdoc at IOP Bhubaneswar, and yeah, I really like this paper, so have fun, guys.
Thank you. Yeah. So hi everyone. Today I'll be presenting this article that started during my BSMS at IISER Mohali. So, however, although like I said, it started with ants, but we could not continue with ants, and then we moved to general autochemotactic system. So I'll just discuss about that. So, just a second. Not able to. So, but now, is that plug thing coming again?
And now it's gone. Perfect.
Okay. Maybe that was the reason. So yeah, so I'll be talking about like what are the phases we observe when a random walk occurs? I'll talk about active random walkers that they when they deposit some markers or say chemical and also follow them. So this work started during a summer project during my BSMS, where if you can see, there were two ants, and we started with tracking them. And as you can see here, the other and the second at which went later, it followed the first ant. And then from there, we also tried to see from the movement. Of course, we also could not see the chemicals, not track them. But from the movement itself, you can see it followed it, although it was not present at that moment. So we also tried to calculate how much of it like followed the trail, with what probability it tried to follow the trail that the other ant had led. But before that, like I said, we could not continue with that. So, and before that, I want to share, let's say, why ants, but this already has been talked before. Here, however, we are focusing on the foraging patterns, and in the foraging, the autochemotaxis or the pheromone plays a crucial role in forming it, or even moving the food from the source to their nest. And so autochemotaxis refers to the ability of a system to move or navigate in response to self-generated chemical signals. So chemotaxis, if you have already seen, but sorry, chemotaxis you might have come across, or phototaxis, where the movement is towards a chemical. However, here the chemical is generated by the agents themselves. Apart from ants, there are several other systems which follow such a trait, such as human trail formation. So this is a picture from IISER Mohali. So initially, when I joined in first year BSMS, there was no such trails. However, with time, this trail developed, and now there is a concrete road also. This is at a higher scale than ants. But if you go to lower scale, so um, uh, this is a video where they were looking at Vibrio cholera, where you might have heard of biofilm formation, which is also involved in some kind of communication via chemical deposition. Here, the difference was that there is some aggregate formation. So, what I want to say is that this autochemotaxis is present at different scales. Naturally, also in synthetic system, also people have seen, or in simulations also. This has been seen both in where the chemical can be attractive, or this is a video where the chemical is repulsive. So there is this self-caging that they observe. Now the question is, how can we model them? To start with, there is um, yeah. So there is this active Walker model, which was introduced much earlier. This can the model says that it consists of agents or workers that where they can change their local environment, and this in turn can influence their motion at a later time. So this is also in autochemotaxis also we observe the same thing, where they deposit chemical, so they change their environment, and this in turn can drive their motion at later stage. So this model could reproduce many patterns at different scales. Here in this work, they had also started with active walkers, in fact, active random walkers, and they showed that if you have, let's say, here is the nest, and then they have these food sources, and then how with simulations how this starts to form this network. So even like they had different distributions of food. One is like they like they had at both the ends, or let's say at different distribution, how this trails emerge with time. They looked at it, and they could produce these branching networks that one sees in ants. And so to begin with, we started with this model, and in our model, we have active random walker model. So the walkers could have some preferential direction. Let's say humans, let's say you see some target and you have a direction to follow. So there we have, so other directions are less probable. Even in ants, it can happen. However, what we are focusing on is active random walker model. So without the environment influence, the walker will be moving in random directions. So I'll move to the questions that we are interested. So as we see, we want to understand how this time delayed interaction. So it might happen since the chemical can persist for some long time. So this interaction can be time delayed, and this interaction is also local. The agent or the worker can detect the environment locally, and also it can modify it also locally. So with such type of interaction, how they form like patterns or what kind of behavior it emerges from them, we want to understand. So first is a single worker. What in such setup, how a single worker behaves following its own chemical trail. So this is the self interaction, you can say, and what kind of trajectory it can develop, that we'll see in next. Then the next question is to add many particles. So there will be interactions, and with those interaction, what kind of collective behavior emerges. And second, and then the question comes, can you understand the mechanism of how this behavior are coming from, or can we also quantify these characters? So, okay. Now I'll be starting with the single walker model that we had. So here we had considered a triangular lattice. One can consider square lattice also. I had tried that. There is no qualitative difference as such, and we had reflected boundary condition. So the walker can go to the boundary and then it reflects back, because initially we wanted to start with a setup. There will be some confinement. Because of that, we had started with a reflected boundary condition. So to begin with, without any chemical, the particle will have equal probability to move. So this is a lattice setup. So the particle can move to one of the 6 neighboring sites with equal probability. So if you normalize it, then it will be 1/6 for each lattice site. next, as the particle starts to add on chemical, it will have a bias, and we are considering attractive chemical in this. So it will have a bias towards higher chemical concentrated sites. So as it moves, it will let's say it moves to the higher concentration, then it will deposit a chemical concentration of unit alpha, and there can be evaporation of the chemical as natural decay follows. So there is decay of this chemical with a rate beta. So as you can see here, the form we have chosen is C by 1 plus C. If it is completely like if it goes to the highest concentration always, it would have been proportional to the chemical only, but we have put a restriction. So it could be due to the limitation in receptors. So let's say there are findings also where so let's say bacteria per se, there are the receptor sites could be limited. So that gives a saturation to the to the detection of the chemical. That's why we have this form C by 1 plus C. So when the chemical is less, it follows linearly. However, when the chemical is very high, then in that sense, the probability to move towards those chemicals will be saturated. So it will follow a constant rate. And this we'll see with this form how the behavior changes. I hope the model is clear. Um,
I had a question.
yes.
So, what is the meaning of R minus RW here?
It's a delta function, so it deposits only where it is present.
Oh, it's
So
a delta function. Okay,
RW,
okay, okay,
yeah,
okay, yeah. Okay. It seemed like delta is a parameter. Sorry. Okay.
sorry, yeah,
So
maybe my
basically, it
presentation.
deposits only at. So
Its
what is
current
RW,
side.
by the way? Okay,
RW
R.
is the position of the walker here.
But which position? It's the current, or
Current
I mean,
position, RFT.
current position. And what is R then?
R, this R represents any R in this side. So the position R is like any side. Let's say here if the ant is present, then it will be 1. If it is not present, it will be 0. So like
Oh, so basically, you're saying that it will deposit the chemical only at where it is, right?
right.
Okay, okay, okay. Okay, okay.
Yes.
So will
So
it be, it is not a function of, so it's only a function of some constant, is it? Alpha, which is,
alpha here we have taken it constant, but
so it
you are
does not,
right.
yeah,
Yes.
yeah, it does not depend on any other factor like
So
some
in the
stimulation or
like
something.
when we went to the many walker part, there we have some constraint. We thought of something, and in
Oh,
fact that constraint made it
okay,
like
okay, okay. So
just.
here there is
But
no
here
as
only
such, hmm.
yeah, no
No, no,
other
nothing it is getting attracted to or something. It's just laying,
uh,
uniformly everywhere.
wherever it goes. So
Yeah.
it gets attracted towards the sites where chemical concentration is high. That is here. So the probability of moving, so the movement has this chemical dependence,
Hmm.
but the deposition is assumed to be constant. So in this setup, it is assumed that the ant has enough food, all the environment conditions are optimum so that it can lay chemical in the
I
simulation
see.
time
I see.
frame.
Okay. Interesting. Okay. Great. Great. Thanks.
Okay. So I'll just tell it once again. So the movement is biased to the chemical it deposits with this form, and this is attractive, so it goes towards higher chemical side, and the chemical is being deposited by the walker wherever it is present. So the deposition concentration is alpha, and this concentration can also evaporate. That is an external parameter. It can also evaporate, so that evaporation rate is beta. In our simulation, we are focusing on these two parameters, how these two parameters are changing the behavior. So alpha, at which it can deposit the concentration, and beta is the evaporation or removal of the chemical. Uh, So if we look at the trajectory, so this is the trajectory of a particle at this alpha 0.05. So in both the cases, we have this beta, which is the decay rate of the chemical constant, and alpha is less here and high here. Here you can see, if you look at the trajectory of the particle, and this is the chemical configuration at low alpha, when so you can say when the alpha is less, the chemical is less, so the attraction is also less. So here we have a more extended trajectory structure, whereas if you increase alpha, so you are increasing the chemical, the trajectory is like compact condensed form. So this we expect as the chemical is trapping the particle. So it forms a global or a closed structure, whereas when the chemical concentration is less, the strength of this attraction is less. So it forms nearly extended, almost like a random walk. But there are instances where it can also get trapped. Now, this is something we observe qualitatively. Now, how we can quantify it? To quantify it, as you might be aware of, that while modeling polymers, we start with often we start with random walk, or even in polymers in a solution, there is a self interaction, and this can be, so the trajectory can be mapped to polymer configuration. So we, for this reason, we made analogy with polymer, and we calculated the radius of gyration. So like I showed here, we have a different decay rate, and I changed the deposition. So the alpha is the deposition concentration at which the particle is depositing. Alpha higher, meaning chemical higher, so the compact structure that I just previously showed. And when alpha is less, the extended structure, so radius of gyration will be higher. So this is a very good order parameter, you can say, or quantifier to differentiate the trajectories of the walker at different parameters. However, here if you see, when the decay rate is very, very less, we see a re-entrant. So the radius of gyration is decreasing, and after a certain point it starts to increase. This is something we found it interesting. The reason here is so if the chemical this form that we have taken is proportional to only concentration, let's say, then the particle can get trapped, whether you meaning how much ever you increase the chemical concentration, the particle will get trapped. Or when we have this C by 1 plus C, we see that after a certain alpha, it starts to expand, and this is a typical this thing trajectory configuration. When you have higher alpha, more chemical, we expect a lesser trajectory. However, it expands more. So you have a higher radius of gyration because of the saturation effects. So with the saturation, what the particles is like, even if the chemical concentration is high, the particle can detect the difference, and that difference because of 1 by C factor, the difference is not much. So that saturation plays a very big role here, and the particle only detects roughly uniform environment. That again brings it to the random walk-like behavior, and it starts to expand, and thus the radius of gyration starts to increase again. Here one can see how quantification helps in understanding the behavior also. And this is for the radius of gyration. Here, however, the effect is not that pronounced, because at the decay rate also plays a very high role here. So at very less decay, you have a higher radius of gyration, and very high decay, the chemical evaporates much faster, so you have less radius of gyration. And then we wanted to see this change from this extended structure to the compact structure, what kind of crossover it is. For that, we had the probability distribution of both the radius of gyration of the trajectory of the walker and the chemical configuration. Here, if you can see, the radius of gyration shifts that we already saw. However, we do not see any coexistence. So in general, in first order transitions, we see coexistence of both the phases, both the let's say here there is like extended coil-like structure, and when you have alpha high, then you have a compact globule structure. This phase, if you in this distribution, if they would coexist, then it would be a first order. However, the absence of it, we call it a continuous transition. Then then we build this phase diagram. For to see for different parameters. As we had seen earlier, for a given beta rate, if we increase the alpha or the deposition concentration, the radius of gyration starts to decrease. So it goes to a coiled extended structure to a global structure. At very low decay rates, the radius of gyration decreases, and then it re-enters to the coil state. So the RG starts to increase again, and this behavior is kind of similar in case of the chemical as well, but the re-entrant part is not very visible here in terms of the chemical radius of gyration. Next, our goal, okay. So far, we have looked at the structure of the trajectory. And now we also know the structure is often associated with the dynamics. Now let's look at the dynamics. For that purpose, what we did is we calculated the mean square displacement at different alpha, which is the deposition concentration. And what we observed that at initial phases, so when T was less than, let's say, 1000 or something, in that phase we looked at how it scaled with T. So we fitted with T to the power nu. So nu decides whether the behavior is diffusive. So if nu is 1, then it is treated diffusive. If nu is less than 1, it is subdiffusive, and nu is greater than 1, it is superdiffusive. So here, since the chemical acts like a trap, we expect a subdiffusive behavior. So as you see here, the exponent, it starts with roughly 1, and then it starts to decrease. So we see subdiffusive behavior, and then again it starts to increase. This is also a signature of the re-entrant transition that we saw earlier, where the saturation plays a role here. So as I'm changing alpha here, alpha increases the chemical concentration. As the chemical increases, the C by the 1 plus C, the denominator plays a very big role, and there C by 1 plus C, if you see if C goes high, then it is nearly a constant. So the effect of the concentration is not seen here. So it behaves almost, or it goes towards the diffusive behavior again. Now, this is for short time scale behavior. For intermediate time scale, for higher value of alpha, we see that the particle's motion is almost goes to a halt. So it's almost stationary, or it is trapped. So this is because of the higher chemical, so the particle gets trapped. But if you see for longer times, all of them are showing diffusive behavior. This shows although the particle gets trapped for intermediate time scales, however, if you look at longer time scales, it gets out of the trap, and it shows this diffusive behavior at very long time. So the correlation with the chemical also goes away, and then at long time we expect because long times these scales go beyond those regions of trap, and it escapes, and all of the particle are different alpha, so diffusive behavior. Now, Next was to look at long time behavior, how it changes with alpha. So we also tracked the long time diffusivity. So since they were diffusive, this delta r square t goes as let's say a times t. Since it is diffusive, t to the power nu will be 1. So a tells the effective diffusivity in this case. And to study that, we started with a mean field description. And here, if you can see, we started with a Langevin picture where the chemical was a drive, gives a drift to the system. So phi here represents the chemical concentration, and chi is the mobility at which it goes towards the chemical concentration, that is phi here. And since without the chemical, or even there is a presence of the particle can also move with a random fashion. So this represents the Bayer diffusion, or without the chemical it can move in random direction. So the noise represents that random walk behavior. So there will be competition between these two. So the noise this will try to move the particle in a random fashion. So, however, this will try to bring the particles together via the chemical. And so now to compare or make analogy with our simulation. So here, as you can see, this is a velocity which is in a discretized fashion. You can write this, and this is equal to so probability. This represents the velocity in terms of the simulations. And if you substitute this in terms of the chemical, like I had told, P goes like C by 1 plus C, and with some approximation, this follows this form. When we equate this, we find that chi, or the mobility, follows in this fashion. So if you, in general, this mobility is taken to be a constant. Here we find that this depends on the chemical concentration in this fashion. So sensitivity goes down as we increase the chemical concentration phi. Now, moving to the co-current picture, here again the density you can think of like the trajectory picture, and this has two contributions. One is because of the diffusion, and another is because of the drift, because due to the chemical deposited by itself. And the chemical has this dynamics where the particles are depositing chemical with red alpha, and there is evaporation with red beta. And here the chi is taken from the previous calculation we had, and substituting here, and then also we assume that the chemical the dynamics of the chemical is much faster. Within those approximation, when we get a relation with the rho and phi, so the density of the particle, trajectory, and the concentration, when we substitute here, we get a form which is similar to what we see in a diffusion equation. And from there, the effective diffusivity that comes out follows this. So without the chemical, it will have the Bayer diffusion, and as we add on chemical, it has a so it decreases, and that decreases is telling is kind of like anti-diffusion. So it instead of spreading, it tries to bring them together. And this form we then compared with our simulation that I just told, that at long times we extracted the effective diffusivity, and these points are from the simulation. And when we with some fitting parameters, so we showed that the behavior follows very well with what we derived from mean field description. And so this tells that these are the minimalistic mechanism that we see in our simulation. Then we also did linear stability analysis of these equations, which for pattern or the instability condition is of the following form, which actually is related to the this only. So this indirect, if you substitute chi and everything here, you'll get back the same equation where d effective turns out to be negative, and that is the condition for instability. In our simulation, we do not see the negative effectivity. That That is because this lambda, which is related to the sensitivity again, is for that we require this, and we do not have the parameter is larger in our system, and so this is not allowing for that localization that this the negative gives. Therefore, we are not seeing the negative value, but to some extent we can explain the behavior with our mean field description. So this is a good theory to match with our simulation. So if I conclude, in our particle simulation, we saw that when the particle gets attracted towards its own chemical, then it gets trapped and it forms a globule-like structure that we capture with the radius of gyration trend. So the radius of gyration decreases with increase in alpha, which is the deposition concentration. The chemical increases with alpha. However, we also see a re-entrant transition where increasing chemical concentration leads to from extended to a globule, then again extended structure. And then we also tried to build a mean field theory which captures the simulation quite well. Next was to go with many walkers. This is not the focus of this talk, but when we went to many walkers, we saw many different behavior. These are some of the phases that I see with many walkers. Although we had, like, you asked the concentration that it deposits the alpha. Now here we had considered that so alpha depends on the crowd. So alpha, the particle deposits only when it is moving or when it is surround, because you can understand when the chemical is attracting, it will attract many particles towards a local site, and then that can give rise to crowding, which will stop their motion in some way. And that time we put this constraint that the particle will not deposit if it is surrounded with this crowd. And this led to this interesting network-like structure. And we also saw that this has similarity with blood vessel growth, and this is using a cellular pot model, and you can say this is our simulation result. The dynamics matches very well, and also it has related to the mechanism that we can discuss later maybe, is in that same way. So here they have contact inhibited chemotaxis. So when they were in contact, here the endothelial cells were in contact, they were not following chemotaxis. Here in our case, if they were in contact, then they are not depositing chemical, and we saw that the dynamics looks very similar to them. I will not focus on many workers, so I'll just move on to questions.